Heavy duty transportation is one of the big areas that we're facing right now. And globally, transportation contributes about 14% of the greenhouse gas emissions, with about 25% of that in heavy duty. So we currently have consumption standards in place in the US, China, the European Union, Japan, and India, with standards under development in Argentina, Brazil, Mexico, and South Korea. In terms of zero emission heavy duty trucks and buses, China is a clear leader with over 350,000 zero emission buses and over 12,000 zero emission trucks. If we now go from the world stage to the US, transportation contributes about 28% of the greenhouse gas emissions, mostly in light duty. But heavy duty contributes about 23% of that. What's worth noting here is that the medium and heavy duty contribution is larger than the next groups combined: marine, rail, and air. So this is our goal. California has some of the most aggressive heavy-duty decarbonization policies. Here's the one for the buses that's being very transformative, which is the Innovative Clean Transit Regulation that was enacted by the California Air Resources Board. Starting in 2023, 25% of new transit bus purchases have to be zero emission. And this continues until after 2030, when you can no longer purchase a diesel bus. And by 2040, the complete fleet has to be zero emission. The parallel to that for trucks is the Air Resources Board's Advanced Clean Truck Regulation, which states that beginning in 2024, manufacturers have to start selling a certain percentage of their new vehicles as zero emission. Finally, last year, Governor Newsom issued an executive order stating that all drayage trucks have to be zero emission by 2035. And by 2045, all heavy duty vehicles have to be zero emission where feasible. Transforming an entire industry is really challenging. This transformation will actually affect all of us, as heavy duty freight transport is the main vehicle that we transport freight across the whole country. So if we are to be successful, we need to optimize across the different options. We are all in this together. To shed light on the two leading approaches to zero emission heavy duty vehicles, we have compiled an amazing list of speakers from the heavy duty transport industry in trucks and buses. They will help us understand the trade-offs of two of these leading approaches, which is the battery electric and hydrogen fuel cell electric vehicles. So without further ado, please help me welcome our first speaker, Ash Corson from Toyota, the Senior Manager of Electrified Vehicles and Technologies. Over to you, Ash.
Thank you so much, Jimmy. Appreciate the kind introduction and the opportunity to speak before everyone today. Bear with me, I'm gonna bring up my screen here for everybody. Hopefully you can see that now. So I'm going to give you a snapshot of some of Toyota's activities and efforts in the electrification space. And as you can see from this opening slide and well described by Jimmy and E and Naomi, electrification, there's a lot to it. It's a holistic challenge. And you can see from all the mobility modes, the vehicles on this first slide, as well as the technology behind them, hybrid electric, fuel cell electric, battery electric. There's really a lot going on. That's because of that diversity of customer need across operations, duty cycles, facilities, regions, energy processing. There's so many unique qualities to each customer set that you really need a portfolio solution set. The other thing too is that it's an energy transition, right? It's not just simply flicking a light switch. There's a time component to all this. There's an asset component to this. So really electrification is helping customers in their existing asset base and operations transform to zero emissions in the most intelligent way possible. So I think well described again by E and Jimmy, we're all quite aware of this need for transformation, carbon reduction. It's a severe need, it's growing and it's global. And the solution, importantly, has to scale across these fleets, facilities, and port type ecosystems that I mentioned. That solution need is also accelerating. On the public's front, you see a lot of stakeholders accelerating their call to action for zero emissions vehicle adoption at scale. As a result, private industry is really pivoting to add these scalable electrification solutions. And one of the most promising is the topic of today's workshop is hydrogen and its fuel cell electric scalability. So I think maybe before the pandemic even, which has contributed to the acceleration, maybe 2040 was the target for zero emissions introduction in some of these leading global markets. And I'd say that's been pulled ahead now, probably to 2035 and even 2030 in some sectors, as Jimmy outlined. So for Toyota, we really, again, this supports kind of that opening slide, a portfolio approach that's required again, and that's simply because there is no silver bullet, one size fits all solution. There are so many different customer needs and operations and duty cycles that again requires that progressive approach. So for us, it's not an either or conversation, it's an and conversation. We need hybrid electric to help the transition. We need battery electric for zero emissions. We need fuel cell electric for scalable zero emissions. So as you see in the blue area on the right, as that scale increases and you become higher range and higher cargo needs, higher performance, including cold weather, better uptime, higher throughput, and hydrogen with its throughput and scalability and fuel cell electric really comes into play. So diving a little bit into the bones of fuel cell electrification and the light duty, Jimmy rightly mentioned that the transportation sector is a huge contribution to emissions, and the light duty and heavy duty in combination are the two big areas. So it makes sense to have a technology that scales from light duty to heavy duty. And on the left, you see the quick mechanics of fuel cell electric. It's basically two inputs. There's hydrogen, oxygen, and it's electrochemical reaction at the stack. You get water vapor and electricity for electric motors as the two outputs. And it's very modular. It's based on our hybrid architecture. So take out the internal combustion engine, put in fuel cell stack, take out the gasoline or diesel tanks in the heavy duty example, and put in hydrogen tanks. And the chicken or egg conversation is quite real. On the right, you see the map of California and all the hydrogen stations. Infrastructure for any of these zero emissions electric technologies is the key enabling factor to that. We launched our very first Toyota Zero Emissions Fuel Cell Electric Mirai about 6 years ago in the California market. There were 2 retail stations for hydrogen at the time. Now there's 44 and growing, and in the next 2 years, that's going to triple in size. So thanks to the state of California's leading progression, enabling, 120 more stations are coming online, along with heavy duty stations. We've already progressed those as well with our colleagues at Shell and Kenworth. So there's a lot of activity happening now on the national level too, in terms of starting to seed other regions with the hydrogen infrastructure. That scalability, again, of the technical architecture really gives you a couple of benefits. Modularity is a key one, performance bandwidth is a key one, and plug and play is a really key one, I think, especially in the heavy duty industry, minimizing the disruption. Such a mature industry in the sense with a diesel based architecture. So getting to zero emissions as needed really requires a minimal disruption. And so we were able to upsize 2 of our light duty fuel cell electric architectures into a Class 8 truck, so 80,000 combined weight. And the progression of that, about 3 years ago now, we introduced the first truck with about 200-mile range in Class 8, and through Kaizen, continuous improvement in packaging, performance, and integration, we upped that to 300 miles and improved the package. And now with our colleagues at Kenworth, and you'll hear from Brian in a few minutes, we're rolling out 10 of those with the state of California. What that looks like is really important. It's at one of the world's largest ports, I think the 9th largest, the ports of Los Angeles, Long Beach. So we're rolling these 10 trucks out at scale now with 4 different operators, including UPS and Toyota itself. Importantly, across 3 duty cycles. So we have car carriers, we have local kind of UPS type delivery, and then we also have drayage, which, as Jimmy mentioned, is one of the key needs here in the state of California and globally. The variety of drayage routes in terms of the cargo, often the fleet drivers and operators don't know what they're picking up and where they're delivering until they actually get their container at the ports. And so that necessitates a versatile, flexible machine, if you will, that can go a lot of range if needed, or it can go up high grades if needed. A lot of variability in those routes, and fuel cell electric with its higher range is a good fit for that. We're continuing to progress. I think on the left you see these first generation trucks. I think Brian was actually at the wheel for some of this, proven in a variety of conditions, including at high altitude at Pikes Peak. And then we were already actually into our 2nd generation system. In the past 2 months, we actually launched our 2nd generation light duty product, the new Mirai, which is a beautiful game changer, about a 10x increase in scale. And we just shattered our volume sales record this last month. So many people remember the 2nd generation Prius. Not many people remember the 1st generation Prius, but the first one was very unique little guy, if you will. And the second one was what really hit it mass market. The same thing's happening on the fuel cell electric side. Our first Mirai was, again, testing the waters, and this 2nd generation car that we just introduced is a game changer and is selling as a reflection. So we're taking that 2nd generation system and already implementing it with Kenworth and PACCAR, and then Hino as well, into the Class 8 trucks. So rapid progress. We're also offering modularity, leveraging that, because it's not just a mobility need, really it's a clean power need. I think Ian and Jimmy both mentioned this as well. There's need for this in the harder to abate areas, the stationary power generation, the rail, the marine, the air. So we're introducing kind of modular cubes, different sizes and shapes and outputs to help customers do that. Infrastructure, I've stressed several times, and again, for a good reason. All of this transition to electrification, this e-growth, really has to, again, be enabled and supported by a flexible e-infrastructure that can scale as, again, those fleets, that time component that I mentioned, as fleets shift their asset base over time from internal combustion to battery electric and fuel cell electric and hybrid. You need a flexible infrastructure that can do that, because as we all know, infrastructure is an expensive investment. We're doing that ourselves as Toyota, installing a tri-generation plant at our port facility in Los Angeles area. Giant stationary fuel cell takes biogas and converts it to renewable hydrogen for fueling fuel cell electric vehicles, trucks, cars, forklifts, etc. Also can be used as energy storage, but also produces renewable electricity for battery electric vehicles, and also for the facility itself, and even exporting back to the grid. So again, it's not an either or conversation, it's an and conversation. I think he already had this great chart from the DOE on the left. It's a wonderful thing. Again, leveraging our current national assets in terms of the electrical grid. We need to bolster that, strengthen that, grow that, as well as our natural gas infrastructure. Hydrogen can play a key role in both bolstering these two, the electrical grid and the gas infrastructure, as well as harnessing it in many versatile ways, capturing renewables, using energy storage, and then also fueling vehicles and returning electricity back to the grids as needed. On the right, a little bit of a smaller graph, apologies, but long story short, the US as a nation is quite well suited with its favorable solar and wind and natural gas reserves to have hydrogen as a key part of the transition. And my last slide, again, just pulling back to the full global picture, a lot going on, again, as you see, but there's maybe 3 key messages. One, that global momentum is really increasing towards hydrogen. China, Korea, Japan, Europe, North America, all increasing hydrogen production for mobility. I think that's a key point. Hydrogen has been widely available and produced, and it's part of the industrial ecosystem for a century now, right? Most of that's for the more industrial kind of refining type activities. Unlocking it now for mobility is the exciting momentum that we're talking about. And these places at scale, like China, is arguably, again, the quickest example that hits the wall first. It's relatively easy to convert a few vehicles or a small fleet to electrification using battery, for example. It's a lot harder to convert an entire port ecosystem or a country to electrification. So hydrogen really is needed as well. And then as a result, there's been a lot of investment and a lot of things coming online now for production of hydrogen for mobility, as I mentioned, and also the stations themselves, both light duty and heavy duty around the world. So in summary, again, trying to keep us on track on time-wise, hydrogen is a real key to this energy transition to electrification. And it really enables scalability and sustainable electrification, which as E mentioned from the outset, those are some really key important tenets. So thanks. So happy to answer any questions later, but I appreciate the time. Thanks so much.
Thank you, Ash. I'd like to then bring up our next speaker, which is Aaron Gilmore, the Vice President of Electric Truck Division at BYD Motors. Aaron?
Yes, thank you, Jimmy. Let me bring my screen up here. Right. Thanks again, Jimmy. Happy to be a part of the discussion here today. And just like to start off by quickly giving a little bit of a description of BYD Motors. Again, I'm Aaron Gilmore, Vice President of Electric Truck Division for BYD in North America. And just kind of giving some quick facts about BYD. There's over 220,000 employees globally. We have something of the order of 200 million square feet of manufacturing space globally, including manufacturing space here in California with a manufacturing facility in Lancaster that spans over 550,000 square feet, where we're manufacturing buses and trucks for heavy duty applications. Right now, we've sold over 13,000 electric trucks, heavy duty trucks worldwide, and over 65,000 electric buses. And BYD's group revenue was around 24 billion last year, and we're an ISO 9000 certified manufacturer. Taking a quick look at the business divisions and what BYD does, of course, there is commercial vehicles like we're speaking about today, heavy duty electric trucks, heavy duty electric buses, forklifts, passenger vehicles, all are EVs. There's a consumer electronics division, as well as a batteries division, and essentially stationary energy storage, as well as a solar module division. And then most recently, as some folks might have heard, BYD is involved in a SkyRail Sky Shuttle product as well that's all electric, and was recently successful in being named an awardee to develop a project in Southern California. In our manufacturing facility in Lancaster, we have over 750 manufacturing jobs. Those are union jobs, and work with the SMART union down there and Jobs to Move America to bring these kinds of positions to the United States. And overall, I think what's important is to understand BYD comes with its core competency in batteries. It started as a battery manufacturer back in 1995. If you had one of those cell phones back in the late 90s, it probably had a BYD battery inside. And the company has moved into electric vehicles in the early 2000s. So we've been at this for some time now. And perhaps maybe one of the most interesting points is that in these heavy duty applications, we use an iron phosphate battery chemistry, lithium iron phosphate. And there's a lot of reasons for that. There's obviously a lot of different chemistries that are on the market, and every manufacturer is striving for things like more energy density, more cycles, and looking for ways to make those batteries safer and safer. And one of the reasons that we use this battery for this application is because it cannot enter into a thermal runaway event. Just the chemistry itself prevents it. Even if you set it on fire, you puncture it, you can do a number of things to this battery, and you can't get to that type of event where the energy input just keeps increasing and the heat keeps increasing to where you can really have damage. So overall, again, the core competencies of BYD are the battery technology, electric drivetrains, electric motors. So again, this is where we've been for a long time. And in fact, we're supposed to be at 75 gigawatt hours annually in battery capacity in the next 1 to 2 years. Just a quick bit on our buses, electric buses. We're at about 500 buses deployed, electric buses in the US, and over 63,000 buses deployed worldwide. Our low floor battery electric transit buses that you see here on the top of the screen have all gone through the federal testing at Altoona with high marks. So the 30-foot up to the 60-foot buses have all passed that testing, and we're entering in a phase where we're starting to test the low floor commute coach buses. In terms of some of the charging options, on the bus side, we use both an AC and a DC charging option. And that is, again, for flexibility, depending on certain situations. We have an overhead charging option, and we've also deployed the in-ground inductive charging type solutions for buses. On the truck side, it's fairly similar. We don't do any overhead, but there is an AC and a DC charging option. And we're also about to undergo our first project in-ground inductive charging, actually at the Port of LA, in a project coming up. Since we're at Stanford today, virtually, we've also deployed 30 buses with Stanford University, and I think they've been in operation since about 2015. So both 30 and 40-foot buses here at Stanford. Moving to electric trucks, really what we've focused on, and goes along with what Ash said about this is a transition, and you're having to fit the duty cycle very specifically to the type of technology that you're using. We've focused in on our heavy duty applications that really make the most sense near term for electric trucks. And that is terminal operations, both yard trucks moving containers around the yard, and drayage operations that are regional hauls that are out and back. Those are great applications. Refuse collection, which of course, kind of one of the most inefficient diesel areas that you could have, with all the stop and go, all the lifts and compactions, probably one of the lowest gas mileage vehicles you'll get in a diesel. Makes great sense for electric. And then in distribution and logistics as well. Again, sort of regional hauls or in-city urban drop-offs where there's a lot of stop and go. Those are the applications that really make a lot of economic sense to go electric versus diesel, and these all have great, obviously, air emission impacts. To kind of get into a little bit of the details without diving into every vehicle that we have, I thought I'd just kind of throw up a few case studies. At BNSF Railways, we have some of our yard trucks deployed. They're easily doing the duty cycle there, ranges from maybe 10 to 15 hours. And really, those trucks are always near a charger because they're in a yard, but they essentially can go multiple duty cycles. I've actually seen at ports where these trucks have gone, 2 full duty cycles. They can even go to, or 2 full shifts. They can even go 3 shift days, again, with some opportunity charging and work throughout the day. So again, it's a very well-fitted application for electric. Here's an example of a Class 8 refuse truck in San Francisco, taking on the hills of San Francisco and doing pickup. This particular one had a normal 8+ hour duty cycle, returns to the charging station with over a 30% state of charge at the end of the day. I've actually seen some of our refuse trucks on the side loaders pick up as many as 800 homes a day. So they're really getting to the point where they can do the full duty cycle. Now, the tough part about refuse is they've been pulling weight out of refuse trucks for decades. So, with batteries, we're battling the fact that you're adding some weight there, and that is probably the biggest challenge, is just to compare to a diesel, is the weight. As they compact the refuse down as much as they can. They've taken all the weight out of those trucks. And so when you add a few thousand pounds, that's a few thousand pounds less payload that you can carry. So, but of course, there are a number of municipalities and cities around the country that are really wanting to go emission free. And in terms of the duty cycle, these trucks perform very well. Another example is a Class 6 box truck that we have, and the Class 6 can be fitted with a refuse body as well for more inner city applications where you need a smaller truck. This example, again, is kind of regional haul, drives over 100 miles a day. It's actually one of our first generation trucks in this model, been on the road since 2017. And again, deals with significant grades and returns back to its home base with greater than 20% state of charge. My final example is a Class 8 tractor. The one, if you can see the one behind me in the screen, is a third generation. This is a second generation for GSC Logistics out of Port of Oakland. They're running drayage, running from Port of Oakland over into the Stockton-Tracy area. It's about 135 miles round trip. They're fully loaded both ways to the limit and basically come back with greater than a 20% state of charge as they make that trip. So these trucks really are on the road and doing real duty cycles today. They're not obviously going across the country. That network isn't there, kind of to Ash's point earlier. But there are lots of duty cycles that these kinds of trucks can meet the need to today as we transition to this emission-free type of solution that we're all striving for. And with that, I will turn it back over to Jimmy. Thank you.
Thank you, Aaron. So our next speaker is Brian Lindgren, the Director of R&D from Packer. Brian?
All right, thank you, Jimmy. I will see if I can share my screen here. Each software seems to put things on a different screen, but let me try and see whether that one shows. Am I sharing my screen now?
Yes.
Great. Okay. Thank you, Jimmy. Thanks, Ash and Aaron, for your presentations as well. I think we're all going to be singing a lot of the same messages here as we go through this. I'll just kind of mention that Kenworth is part of PACCAR Incorporated. We're a major heavy-duty truck manufacturer. Kenworth is one of the divisions. Peterbilt is one of the divisions, and DAF in Holland and Leyland in the UK are all part of the PACCAR family. So together we're the third largest heavy truck manufacturer in the world. In North America, in US and Canada, we're the second largest, and Kenworth is probably, Kenworth and Peterbilt share about the same market share. Kenworth is leading the past couple of years. So we've been quite busy in working towards fuel cell and battery electric trucks, moving towards zero emissions. So I'll talk a little bit about these projects. Why are we interested in building zero emission heavy trucks? We'll compare a little bit between battery electric and fuel cell electric, and then look briefly at some lessons learned and where we're going from here. So if we look at the reasons, what drivers are there that are pushing and pulling for zero emission trucks? obviously regulations. As Jimmy mentioned, the California has made some regulations on OEMs to sell a certain percentage of the trucks that they bring into the state to be zero emission vehicles. And then 15 states and the District of Columbia are sharing that same vision. So we'll see that by 2035, a very high percentage of the new trucks sold into those states will need to be zero emissions. California is also now looking at a mandate on the purchasers of the vehicle. So it's not only on the OEMs to sell them, but on the buyers to buy them as well. So that'll be coming. Also, we're finding that our customers are interested in having a green image and showing sustainability goals. That helps them in their marketing and branding. It also helps them to attract good talent to their organizations as well. But I will say that today, zero emission trucks are challenged by a good return on investment. They're more expensive to purchase. Even though battery electric trucks can have a low fueling cost, if you will, the initial purchase price is higher. So until we get our volumes up substantially over time, the cost of these vehicles will be a little bit higher. I'll talk a little bit more on that. So what I'm saying is that we will need to rely on some incentives initially to the manufacturers to help build the development of the trucks and bring the cost to produce them down, and then we'll need to move to incentives that would help the purchaser to buy them. So Kenworth is active in this realm. On the left, you can see one of the fuel cell electric trucks that we're working with Toyota on. And then on the right is an example of the type of truck we're building, a prototype battery electric truck with a wireless charger. And the goal for that particular one-off truck will be to drive from Seattle to Portland on one charge. It's about 170 miles, recharge wirelessly in half an hour during the driver's lunch break, and then make the return trip, another 175 miles back to Seattle, and then recharge for the second shift. So we're working both on fuel cell trucks as well as on battery electric trucks. So let's look at why both. Wouldn't one be a better pick than another? Well, as it turns out, yes, one probably is a better pick than another, depending on what you're doing. So if you're just operating in a small area, as Aaron mentioned, the relatively short hauls of a refuse pickup truck or drayage or city delivery, if you're running under 100 miles a day and staying in your area, battery electric probably is the right choice. But if you're going over 200 miles a day, then the batteries get pretty large. And so if you need to run between metropolitan areas, then fuel cell starts to make a lot more sense. And I'll talk through some of the reasons for that. But the way we say it, as Ash mentioned, there's no silver bullet. There's no one size fits all for everybody. We're going to need both of these technologies to be able to move toward true zero emissions. So let's take a look first at comparing diesel and compressed hydrogen and battery electric trucks on a regional haul kind of operation where a truck does 350 miles on 2 shifts. So they might run 100 miles during the day and then at night take a longer run of 250 miles, 125 out and back. So with today's diesel truck, the fuel you need, probably 70 gallons to do that 350 mile run. The fuel itself weighs 500 pounds. The tank you put it in, 150. So you've got 650 pounds of fuel and tank on board. And with that kind of arrangement, today's trucker can haul about 50,000 pounds of payload and still stay within the 80,000 pound gross combination weight limit that most states have. So if we look at a fuel cell truck, it takes a little bit less load in in fuel, the tanks today are pretty heavy because they're high pressure tanks. But for a zero emission truck, you're allowed 82,000 pounds now. So even though we gained 4,000 pounds, we still are pretty darn close to the same payload with a fuel cell truck that can go that kind of range. Then with a battery electric truck, to go 350 miles, mostly at highway speeds, you're going to consume about 900 kilowatt hours. And so you need a bigger battery than that so that you've got some margin and so that you don't run from zero state of charge to 100% state of charge. So by the time you have a battery large enough to do that, it's going to weigh a whole bunch and you've lost about a third of your payload capability. So as Aaron mentioned, when you get into the longer ranges, it can hurt in terms of tare weight and lost payload opportunity. So there's an advantage for fuel cell there, but both of them are a little disadvantaged against diesel. Now, if we look at productivity, in other words, refuel recharge time, diesel refuels very fast. You can put 70 gallons in under 5 minutes. So that's really not an issue. Compressed hydrogen, 15-ish minutes to put the 55 kilograms into this kind of an arrangement. So that really isn't much of an impact. But battery electric takes a bit longer. Even at 250 kilowatt rate, that's still 3.5 hours to put that much energy back into the truck. So it makes it difficult to do a 2-shift operation if the truck needs to be stationary for that length of time to be recharged. Another issue is that you can refuel a diesel truck at pretty much any truck stop. You can refuel a hydrogen truck at a hydrogen station that isn't on site because you're only there for 15 minutes or so. But a battery electric truck, you're going to have to park it there for quite some time, longer than the driver is going to want to wait for it to recharge. So that's probably going to mean that you have to put in some infrastructure at your truck terminal on your own site. So that means you have the capital expense yourself. So if we look a little bit at cost, Jimmy asked us to include some costs. So these are approximate costs at about 4 years out from now. A diesel tractor might be in the range of $150,000. So by the time we pay federal excise tax and California sales tax, this happens to be in the LA County area, you're about $180,000. Fuel at $3 a gallon is a little higher than that today. Each year you might do $63,000 in fuel. So if we look at a fuel cell truck, they're pretty expensive right now. In fact, at our one-off kind of quantities, they're about double this cost. But over time, we expect by the end of the decade, we'll be getting much closer to the diesel, to parity with diesel. But today, and even in 2025, they're quite expensive. And that high purchase price means you pay a lot in federal excise tax and a lot in sales tax, even though that you're not getting the road benefit for those extra dollars. Fuel cost might be in the range of $10 per kilogram in this kind of time frame. That will be coming down over the next decade as well. So that's a bit higher. So it does cost more to run a zero emission truck than a diesel truck. A battery electric truck, I won't speak for Aaron, but I'm looking at this same kind of vehicle that has the capability to go 350 miles on a charge. Takes a lot of battery, and batteries are expensive today. So again, a high tractor cost and high federal excise tax and California sales tax, but the energy costs are quite low. So about half of the cost on the energy for a year compared to diesel, but the initial purchase price is about 4 times as much as a diesel truck is. So those are some comparisons in the 2024-2025 timeframe, and we hope that by the time we get out into the 2030s, those costs can come down some. But we need to get volumes up and need some incentives in order to get there. Some brief considerations on batteries that you would use in a fuel cell truck. Since a fuel cell truck is essentially, it's got all the same components as a battery electric truck. It's got an electric traction motor and it's got batteries. It's got all the cooling systems. It's got electric power steering and electric brake air compressor and electric HVAC components. Then you add the fuel cell and the fuel tanks. But you can either use a small battery with stronger load following fuel cells. And so that means the battery is lower in weight and it's smaller, but you really hammer it with C rate. But you get a little bit less length of grade that you can sustain and less energy that you can store during regenerative braking. Or you can put a larger battery in, and again, you gain in terms of grade duration and braking availability for regenerative braking. You can typically use a lower cost cell in the battery, but it's bigger and it's heavier. So, and it's more expensive also. So those are some considerations that we're weighing as we go through future fuel cell designs. Challenges that we face in building zero emission vehicles: the supply base is still developing. A lot of the suppliers for this are just getting into the industry now. Their reliabilities are not as high as we'd like. And components are not plug and play at this point. They take quite a bit of development to incorporate them into our truck designs. There are some rather complex architectures for the cooling systems and the electrical and control systems, and we've worked through most of those issues at this point. We're also learning that what the driver needs to know on a zero emission truck is different from what he or she needs to know for a diesel truck. So we're learning how best to present the right information at the right time to the driver. I talked a little bit about batteries for high power for sustained grades. If you're running over the grapevine, for example, you need to be able to sustain high power for quite some time. And that can either come from batteries, or it can come from the fuel cell, or it may need to come from both. So we're still working through how best to accommodate that. And then the fueling infrastructure, as Ash mentioned, there are, I think, 5 truck fuel stations today in the LA area. That's about it for the country. So there's quite a bit of fueling infrastructure that needs to be built out for hydrogen. Again, also for charging, if we do wireless charging, there's not much infrastructure for that yet. But smaller rate battery charging can be done at the 150 kilowatt range, but then that takes longer to charge these big batteries. And as I mentioned, these trucks are expensive. Fuel cells are expensive today. Batteries are expensive today. Onboard hydrogen fuel storage is expensive today. Those costs will come down, but it's going to take a decade or so to do that. And then there's lots of interest, but a lot of concern on the part of the customers regarding the total cost of operation, especially considering that high initial purchase price. Then we've got some research, of course, being the Director of Research and Development for Kenworth. This is where I look, and things that we need to learn more about include: how do we bring the cost down on fuel cells and on fuel cell trucks? How do we bring the cost down on onboard fuel storage while increasing energy density so that we can carry more fuel in the same space and the same weight? We need to look through the hydrogen fuel infrastructure and see what can be done to keep the cost of hydrogen fuel down. Then also we needed some step changes really in batteries. Need to get the cost way down and the weight way down in order for zero emission trucks to be really be able to make them viable commercially. And then also, what do we do about recycling those batteries? What do we do at the end of their life? There's some questions that need to be resolved there as well. And then so far, at least at Kenworth, we've looked pretty much at tractors. But as Aaron mentioned, we need to be able to look at other vocations such as refuse packers and dump trucks and concrete ready mix and utility trucks and a whole host of things that have some very specific body design things that need to be accommodated. So we'll be looking into how to accommodate those. So with that, I'll wrap up and I will hand off to the next speaker.
Yeah, thank you, Brian.
Thank you.
Just a quick note to the audience. A reminder to use the Q&A button. We've received a number of questions. Please continue and use the Q&A button to ask your questions. We have now heard from 3 OEM truck manufacturers, and our next speaker is Amgad El-Gawaini from the Argonne National Lab, who's the leader of the Electrification and Infrastructure Group, who will share with us his thoughts.
Thank you, Jimmy, and hello, everyone. I will talk about electrification of heavy-duty vehicles, considering both batteries and hydrogen fuel cells, highlighting some opportunities and also some challenges. So medium heavy-duty vehicles, they have a wide range of vocations, as you could see on the table at the bottom left, and I will show you why they matter. I mean, and like a previous speaker mentioned, there is no one fit for all. There are some market segmentation. There is some attractive features for each vehicle class, where one powertrain might be more attractive than others, and what underlying factors are there. In general, medium and heavy-duty vehicles are contributing significantly to air pollution, as you see on the bottom right. I mean, NOx emission just from that vehicle class exceeds NOx from all power plants nationally. In addition, we have seen from Jimmy's chart that they contribute also about 23%, about a quarter of our greenhouse gas emissions from transportation, 370 million metric tons of CO2 emitted in 2019. So this is actually where I would like to start on the vehicle side, and we'll get to the fuel side. So if you look at battery electric vehicles or trucks, I mean, I will compare only the powertrains here. I mean, $1 per kilowatt hour represents a slope on overall cost for powertrain on the vertical axis, storage amount on the horizontal axis. Hydrogen storage is always lower cost, and therefore the slope is lower, but because hydrogen fuel cell trucks are less efficient than battery electric truck, we need really to account for that, adjust the slope with the fuel economy ratio, because I will need more storage for the hydrogen truck in kilowatt hours compared to a battery truck. Furthermore, a hydrogen truck will require some fuel cell. You can consider it an overhead and a battery for the hybrid feature to be able to maximize the efficiency. So this will lift the blue curve to intersect with the battery curve powertrain at some point. That point may shift right or left depending on what I just mentioned to you: the cost of the battery, the cost of the fuel cell, the cost of the hydrogen storage tank, and the fuel economy ratio. All of these will play where that intersection point is. But there will be some intersection point, and you will see to the left, the blue curve is above the green, and this will be consistent with low onboard energy use, low daily fuel use, and to the right of that intersection point, you will see a high demand for onboard energy storage because perhaps of a high VMT, daily VMT, or a low fuel economy, or both. However, this is not the whole story. Of course, we need to consider other aspects that are critical to the cost of ownership, the lifetime of the energy storage, whether it is a battery or fuel cell, actually over the lifetime of the vehicle, and the more important is the fueling cost or the charging cost, because this will really come, I mean, will be on top of the vehicle cost when you consider your levelized cost of driving. So this will take us to this slide. I mean, if you look on the left here, you will see for light duty vehicle cost is dominant, fuel cost is small. On average in the US, we drive somewhere between 35 to 40 miles a day. So our fuel cost is smaller compared to the depreciation of the vehicle cost over its lifetime. I mean, if you look here, actually on a truck, you will see the opposite. Actually, fuel cost is dominant, vehicle cost is a smaller portion. And it matters really, I mean, not only the vehicle costs according to the previous slide, but actually the fuel costs for trucking could be significant. Of course, this again will depend on your daily VMT, as the previous speaker mentioned, and also your fuel economy. But I would like to highlight here further, it is not just the fuel economy in absence of a baseline. So for passenger cars, if I compare hydrogen to gasoline vehicle, we are talking about a fuel economy ratio of 2.4, 2.5. This gives me much room because a kilogram has the same energy in a gallon. So if I really use a high fuel economy ratio, then actually if I have a $2 a gallon, hydrogen can be at near $5 and be competitive on a per mile basis. If gallon is 3, then hydrogen can go up and so on and so forth. So you get really fuel economy ratio is key. If I go to a line haul, really a longer haul where diesel trucks are very formidable, I mean, very high efficiency, 85% of the vehicle mile traveled is on the highway, actually a high efficiency point for the engine, then we'll see that the fuel cell compared to a diesel might be in the range of 1.0 to 1.2. And that really kind of squeeze us. I mean, if I have a $2 a gallon of diesel, then hydrogen needs to be roughly at par, right? And it's same actually here. So you'll see fuel economy ratio plays a greater role. And this is where it comes the earlier chart that different locations have different fuel economy ratio. And therefore, actually, a hydrogen fuel cell vehicle could be more attractive if I have a high fuel economy ratio, such as buses or delivery vans and so on. I will show you a chart there, but I want you to walk away that fuel economy ratio is key to enable an incumbent because it will play directly into the fuel cost, and the fuel cost is dominant in the total cost of ownership. So I get to the hydrogen. Actually, I want to highlight here, this is a typical hydrogen station. You have some supply, you have compression to lift the pressure, depending on whether this is 350 bar tanks like buses or 700 bar tanks. If you want to put more on board the energy, then I need to lift the pressure here to 450 or 900 bar. If you want to fill fast, you need pre-cooling and all of that. So all of that adds capital. What I want you to walk away with this chart is that onboard storage matters. It will matter to fuel costs, and the fuel costs matter according to our previous chart. So I wanted to take you to a different, a different slide. How I supply hydrogen also matters. This is the same onboard storage I showed in the previous slide. It is 350 bar or 700 bar. But rather than having a gaseous supply, if I have a liquid supply, I can use a pump, relatively inexpensive, very high throughput, lift the pressure, heat exchange, condition, I don't need pre-cooling, I can buffer or not buffer, and then I can dispense directly. You will see this is economically much more attractive option as far as supplying the molecule. So if we want to look further, we can look at some advanced tanks like cryocompressed or even a liquid hydrogen tank. This will be very similar to an LNG tank. I mean, this one will have a high payload, and this one doesn't need even to be pressurized. And therefore, really, your fueling equipment could be much lower cost, and the configuration will be much simpler. So with that, actually, we develop our model. This model is used by thousands worldwide, actually, transit agencies, energy companies, gas companies. So this is really actually bottom-up techno-economic model, quotes from vendors on the components, and then we build it bottom up, tell you what is the dollar per kilogram. This is only for the fueling station. This is only the contribution of the station. On top of that, you need to add delivering the molecule. If you source liquid today, you can get it somewhere between 4 to 6 kilograms, depending on the payload, depending on the distance. I mean, if you do on-site electrolyzer, it could be higher. Of course, you will need some additional storage. If you do SMR, it could be lower, but this is usually a fossil source. In addition, SMR likes to run continuous. So if you have a fleet where you have some fueling, again, you will need some cost of storage there. So this is the fueling cost. This is what I told you, actually, gaseous supply versus liquid supply. Looking at tanks first, let me look at tank, 350 bar versus 700 bar. You want to pack more molecules on board, it comes at a cost. And then your running cost will be significantly higher. If you source liquid instead of gas, really, that jump is less, and you will see the cost compared to a gaseous supply is much lower. So this gives us a hint that liquid actually hydrogen supply is more favorable when I demand more onboard storage, when I demand higher payload, when I have a higher daily fueling capacity. Look at the hydrogen tank. If this tank is being developed, and I know DOE is funding a lot of research on this, We know Daimler Linde really did talk about this tank. Your fueling contribution actually could be less than $1 per kilogram. This will be much more attractive than these high pressure tanks. So fleet size matters too. I mean, 30 trucks versus 50 versus 100. Here I just put like buses actually, but I mean, this is 35 kilograms each. You could see the economies of the scale. Even if you reach a very large number, you add a dispenser, you still really can be at a reasonable cost. Again, liquid supply is much lower compared to gaseous supply. And look at liquid hydrogen tank. Actually, you could even dip the fueling station contribution can be below even $0.50 per kilogram. However, liquid come at some penalty. You have energy efficiency. You talk about 10 kilowatt hours a kilogram. So it is important really when we look at carbon that this electricity for liquefaction should be from a zero carbon source. I mean, California is a low carbon grid. In the Northeast here, there is a lot of hydro, but in other places, it might have a higher carbon footprint. So it is important really when we look at liquid from economics, we do not really kind of have an oversight of the carbon footprint associated with liquefaction. I just want to mention that there are many liquefaction plants coming online because of the growing demand. So this is really the fuel economy ratio impact I told you about. Actually, we just go from a very high fuel economy ratio, even an SMR, a fossil source, because of a high economy ratio for this about 2.7, you will see diesel emissions here per passenger mile actually, or per ton mile, depending on the vocation, can be even much lower, even a fossil source. Of course, if you go green, it is much lower emission. But you see the difference between diesel and SMR hydrogen shrinking as your fuel economy ratio erodes for a longer haul. It might be just at par. And the only way to reduce your footprint will be really to source a green hydrogen. And if you liquefy, you want to source green electrons for the liquefaction. If I move to battery, again, I put here similar vocations. I put here the fuel economy ratio. And again, for some, it is really close to 5 times, while for some, it is less than a factor of 2 compared to diesel. Again, the driving cycle will play big role into your fuel economy ratio, which will play big role on how you can compare to diesel and what unit energy cost, whether it is electrons or hydrogen, you can really break even with diesel on a per ton mile or per passenger mile. Here is the, I mean, again, greenhouse gas emission, very favorable, even with the US grid, where you have the high fuel economy ratio, but when you go to the longer haul, actually, you are roughly breaking even. This is the 2019 grid, US grid. Of course, if you look future, we know the grid is getting cleaner, the picture will be better, but the advantage on well-to-wheel, the carbon emission, will still be significant. Of course, we know the US grid actually is very different in different regions. So here I show you the different regions. And you will see how the BEV in well-to-wheel emission, whether it exceeds or provide benefit, again, is the internal combustion engine diesel. You will see the Northeast, a lot of nuclear and hydro, right? I mean, very minimal coal and a lot of natural gas combined cycle. You can be roughly 40% lower. Similarly, on the West Coast, you have a lot of renewables, a lot of hydro. I mean, and this will actually help you actually also beat the diesel even on a longer haul. I mean, while in other regions, you may exceed, depending again on the grid, as you all imagine, actually, it could have a very different picture for the charging. As far as charging cost, I will defer that. We are developing a similar model to the hydrogen model that we will release this summer. And there I can talk to you with more informative analysis on the fast charging of battery electric trucks. With that, I want to acknowledge the Hydrogen Office, the Vehicle Technology Office, who supported our work in the past. And here are the links to our models. If you are interested in our life cycle analysis model or techno-economic models, they are available for free download. Thank you very much. And back to you, Jimmy.
Thank you, Amgad. So we're going to switch gears again, and now we're going to go from trucks to buses. And I'd like to have Sal Lamas, the COO of AC Transit, now speak. Welcome, Sal.
Thank you very much, Jimmy. Appreciate the opportunity to be here today to share AC Transit experience with Zero Emission Bus. Just want to confirm that you can see my my slides.
Yes, we can see it.
Okay, perfect. So just a brief overview on AC Transit is we are the the largest bus-only transit agency in California, serving about 1.5 million people in our service area of 364 square miles. We operate a fleet of 640 buses, supported by 7 facilities, and a workforce of about 2,200 employees. What you see on the map here, we have 2 zero-emission fueling facilities. One is in our Emeryville facility, which is a hydrogen station. And in our Oakland facility, we actually have now 2 types of ZEB infrastructure. We have hydrogen and also battery charging infrastructure. You mentioned, Jimmy, the innovative clean transit regulation in California, leading the nation on deploying and mandating the deployment of zero-emission bus technology. So in June of 2020, AC Transit's board of directors adopted a resolution approving the AC Transit zero-emission bus rollout plan. The plan provides a path to achieve the goal of transitioning our bus fleet to 100% zero emission by 2040, excuse me. It is a living document. It's meant to guide the implementation of ZEVs into our fleet and help the district work out through the many potential challenges, but with a focus and commitment to explore and implement solutions. The following transition guiding principles were established in the plan. Is to replace the fleet per the FTA mandated transit asset management plan that has some performance targets on how we transition our fleet and replace our aging fleet. Prioritize the ZEB deployment per the AC Transit adopted Clean Corridors Plan, and the Clean Corridors Plan identifies 13 corridors within our service area that services disadvantaged communities. And also to procure ZEBs based on vehicle and infrastructure technology capabilities to meet the service requirements from our routes and our lines. And then deploy ZEB technology that is most efficient and sustainable to operate. And then finally, obviously, we want to meet the goal to transition the entire fleet to 100% zero emission by 2040. So how are we going to do that? I do want to say that I'm very proud that AC Transit has been a leader in advancing zero emission technology since the early 2000s. We have been deploying initially hydrogen fuel cell bus technology. We started with a bus demonstration of 13 hydrogen fuel cell buses, 2 different generations. Since 2006, these buses have been on the road. The most recent ones that we have today have been on the road since 2010. And I do want to say that we have not only met but surpassed the Department of Energy and Federal Transit Administration performance targets for that hydrogen fuel cell fleet. Many of the buses, well over 5 of the buses, achieved over 30,000 hours of continuous operation without failure on the fuel cell power plant. They continue to be on the road today, accumulating well over 3.3 million miles of zero emission service. Now we're in the advanced stages through a collaboration and partnership over the years with original equipment manufacturers and some of our funders and partnering agencies. We're now moving into deploying both technologies. So now we have a fleet of battery electric buses that we added to our service. Currently, we have 7 battery electric buses and 21 hydrogen fuel cell buses that are in the active fleet. And then we're also doing the first ever deployment of a 60-foot hydrogen fuel cell bus, partnering with New Flyer, who has been an excellent partner with us. And what you see pictured here is the New Flyer fuel cell bus, battery bus, and the 60-foot bus. We're also, as we grow our fleet, we're growing the infrastructure capability. We initially started with hydrogen fuel stations at our Emeryville and Oakland facility. We recently upgraded our hydrogen fueling capability at the Emeryville facility by transitioning from compressing gas to now doing cryogenic pumping. What we learned during our study is that it actually surpassed our expectations. Now we can fuel back-to-back 65 hydrogen buses within the same 10-hour fueling window that we do our diesel fleet. in about, and what we're seeing is between 6 to 8 minutes per fill for each bus. We realize that if we can do some modifications on the programming of the facility, we're very confident that number can increase to almost 100 buses. So that's just significant and remarkable. We also have added charging infrastructure in the Oakland facility. We already have a hydrogen fueling station. However, that station it can only fuel about 13 buses back to back. It is the older technology. We're applying for grants to advance that technology into the same design as Emeryville. We also have plans in the Oakland facility to build out charging infrastructure for up to 50 more battery electric buses. So we're pretty excited. We're also excited to announce that we just recently awarded contracts for 20 more hydrogen fuel cell buses and 21 more battery electric buses. So we expect by before the end of 2022, we should have about 70. We should be operating 71 zero emission buses in our fleet. So this is where I get really exciting. And how are we going to learn and know what would be the appropriate way to deploy zero emission buses as we start to scale up and transition into the larger numbers? As I mentioned earlier, we have 640 buses in our fleet. So we're going to have to start to really do a strategic and well-educated transition. In order to do that, we launched our first ever true side-by-side comparison. This began when we had the New Flyer battery bus and fuel cell bus operating together in the same lines, from the same division, with the same operator group, on the same routes, in the same environment, and realized this is a really neat opportunity to look at how zero emission bus technology really stacks up against itself, and also look at the infrastructure. Then we realized, wait a minute, we can actually add more to this study. So we're actually including our diesel buses and our diesel hybrid buses. And we also decided to go ahead and match up the legacy, what we call a legacy fuel cell, which is our original fuel cell buses that, interestingly enough, they have a different design where the legacy fuel cell bus is fuel cell dominant. Fuel cell actually provides the electrical power to the traction drive motors, where the new buses that we have today, the new design, is a little more balanced, where the batteries actually provide the electrical power to the traction motors, and the fuel cell is more of a recharger on the road, if you want to per se, that keeps that bus moving. So it's exciting, and I think what's even more exciting, that we partnered with Stanford University to conduct a third-party, neutral, transparent overview of our data to make sure that we get it correct. We have a lot of experience of doing performance comparison reports over the last 20 years, but it's always good to have someone like the prestigious university and the staff to really give it another once over, and maybe even share some other ideas or other results that they can use the data for comparison of the fleet and the performance of the fleet. So we're excited to say that we have collected the data for the first 6 months. We're in the process right now of reviewing and finalizing the report. Our expectation is to present this report to our board of directors in either May or early June, and publish it publicly for the industry and for the rest of the world to learn from that. That concludes my presentation. Thank you very much, Jimmy.
Thank you, Sal. And I can say that we're very excited to be working with AC Transit on this study too. So I'd like to present our next speaker, which is Jennifer McNeil from New Flyer, who's the Vice President of Sales and Marketing.
Hi, good morning. Thank you, Jimmy. Let me see if I can share my screen here. Please let me know if you can see my presentation.
Yes.
We good? Okay. All right, good morning. My name is Jennifer McNeil, and I'm the Vice President of Sales and Marketing for New Flyer and MCI's public sector business. I'd like to start off by thanking the Stanford team for having me on this panel. I'm thrilled to be here today and speak on the topic of decarbonizing heavy-duty transit. So New Flyer manufactures heavy-duty transit buses for North American cities in all lengths and propulsions, including 3 types of zero-emission propulsion: battery electric, fuel cell electric, and trolley electric. And in fact, our first zero-emission buses were deployed, they were trolley electric buses deployed in 1969. This is a really important and timely topic in our drive to carbon neutrality. And so as Jimmy mentioned earlier in the session, according to the US EPA, transportation sector accounts for approximately 28% of greenhouse gas emissions in America. And light duty vehicles are about 60% of the transportation sector emissions. So public transit has this really wonderful compounding benefit. It gets people out of single passenger light duty vehicles, and it reduces urban congestion and improves air quality. And when you transition public transit to zero emission, it provides a really significant reduction in greenhouse gas emissions in our cities. So I thought I'd start off by telling you a little bit about our organization. Over the last decade or so, through a combination of organic growth and 8 strategic acquisitions, we've actually become NFI Group, which is one of the world's largest providers of mass mobility. NFI Group's extensive family of brands offers the widest range of buses and coaches on the market and is supported by a global team of 8,000 people. In fact, across NFI, we've actually logged more than 20 million electric vehicle miles, and our vision is to enable the future of mobility with innovative and sustainable transportation solutions. So I thought I'd start out by very quickly highlighting a few of these zero-emission products available in North America, and then I'll talk in detail a little bit about the technology and the comparisons. So on March 15th, we introduced the next generation of our industry-leading battery electric bus, the zero-emission Excelsior Charge NG. This is our 3rd generation battery electric transit bus, and it's built on the Excelsior platform. Our Excelsior Charge H2 is a battery-dominant fuel cell electric bus that effectively uses onboard hydrogen fuel cell to recharge the batteries. We also have our MCI D45 CRTE LE Charge. It's a battery electric commuter coach, typically used in transit commuter or express coach service. And we've got our J4500E Charge, which is a battery electric motor coach used typically for tour and charter and intercity travel. On February 26th, we unveiled ARBOC's first zero-emission medium-duty transit and shuttle bus. It's available in 30 and 35-foot models, and it incorporates similar components and technologies to the Excelsior Charge. And lately, the Alexander Dennis E500 EV battery electric double-deck transit bus has made its debut in demonstration service earlier this month in California and Washington State. So as you can see from this map, we've actually been fairly active over the past couple of years, having been awarded zero-emission bus programs in cities across North America. We currently have delivered approximately 750 buses to 40 cities throughout North America, including approximately 30 fuel cell electric buses, which include the ones that Sal has just mentioned. At a very high level, both fuel cell and battery electric technology are on similar trajectories of advancement, both in reliability, performance, weight, cost, and energy density. Since 2012, we've been testing, deploying, and supporting approximately 250 battery electric buses in service. And we've used these lessons learned over almost a decade to drive innovation. All 3 generations of our battery electric buses have been built on the Excelsior heavy-duty bus platform. We offer electric buses in 35-foot, 40-foot, and 60-foot models. The vehicle itself incorporates batteries or energy storage systems located on the roof and in the engine compartment. We utilize proven ZF axles and Siemens PEM motors that eliminate the need for a transmission. The Excelsior Charge NG incorporates 3 distinct high-performing new technologies. First, it integrates battery packaging for the energy storage system designed and developed by New Flyer that lends significant maintenance and operation benefits to the operators. Secondly, the next generation ethically sourced high energy batteries deliver 13% more energy density, allowing us to improve range and weight optimization for the vehicle. And third, we've introduced our latest traction propulsion system from Siemens, the Alpha 3. Our fuel cell journey began back in 1993 with prototype technology, followed by a 20-bus evaluation program in the 2010 Olympics, which helped to lead our current generation platform. Also built on the proven Excelsior program, the Excelsior Charge H2 utilizes the same robust electric propulsion system as the Excelsior Charge, featuring industry-proven Siemens and ZF components, as well as Ballard fuel cells. It's available in 40-foot and 60-foot configurations, both of which are operated by AC Transit. Fuel cell buses use a battery-dominant hybrid architecture where the batteries are large enough to handle the vehicle performance needs, while the fuel cell acts like a continuous battery charger to handle and extend the range of the vehicle. So as you heard from Sal a little earlier on this panel, the comparisons are definitely helping to inform the use of both technologies in public transit. If you can imagine though, the energy consumption and therefore the vehicle range is really highly dependent on climate, topography, duty cycle, and driving techniques. So for transit buses, these are vehicles that open and close their doors all day long and have significant energy draw for heating and air conditioning in extremely hot or cold climates. They're drawing quite a bit from the battery. High-grade motors typically draw approximately 5% more energy than standard grade motors, and regenerative braking can actually recover over half the energy consumption on certain routes. So when I'm asked what the range of a zero-emission bus is, or to compare battery electric to fuel cell, my typical answer is it depends. However, all federally funded vehicles in the United States are required to be tested at the Bus and Research Testing Center at Penn State in Altoona, Pennsylvania. And so since I have a number of scholars in the crowd, I thought I would actually include a comparison chart of some of the test results under controlled conditions. So these aren't real world examples, but I think they're really useful to show the differences. The tests are conducted using a combination of 3 different duty cycles: central business district, arterial, and commuter service. And battery electric buses are sold typically with a variety of energy storage systems. And you can see here that the highest capacity energy storage system is really still only about 72% of what's needed. And in many cities, this is enough to serve most of the routes for the agency, but very careful planning is required to match the vehicles to the service needs. Over the next 24 to 36 months, I could see that gap closing to where battery electric buses will approach the 280 to 300 mile range. Under these same conditions, you can see that fuel cell electric buses have not quite the range levels needed by the industry. Most bus specifications call for 350 miles range. However, it's actually very close in the Altoona testing protocol at 305 miles. And we actually did manage to test one of our fuel cell vehicles to 352 miles back in 2019. So I think we're getting really close with the fuel cell electric model. Similarly, when asked about price comparisons, my answer is always, it depends as well. Heavy-duty transit buses are typically highly custom engineered to meet our clients' specifications. But in the interest of an apples-to-apples comparison, what I've included here is pricing from the Washington Department of Enterprise Services contract. This is a fairly basic specification and kind of a publicly available contract to show pricing. And you can see that the lowest capacity battery electric bus is almost double the price of a similarly configured diesel bus. And a fuel cell electric bus is approximately 2.5 times the price, just based on today's technology. I would like to talk a little bit about price trends, however. Prices are coming down, with the fuel cell electric buses on a greater trajectory, largely due to some cost decreases in the fuel cell themselves, and due to some common technology and manufacturing techniques with battery electric buses. On the battery electric bus side, we are seeing advances in battery chemistry and in energy density. And while battery electric buses are dropping in price for a specific energy storage capacity, since the range is not quite meeting what the industry needs right now, as energy density improves, customers are basically opting for more batteries on board the bus and thus more cost. So if you were to plot actual battery electric prices, you would probably see a flatter curve on the battery electric buses. So these costs are really just dealing with the bus itself. They don't include fueling or the charging infrastructure. And when I'm asked about that, I say it really depends, especially at scale. For battery electric buses, whether you choose depot charging or an en route charging strategy, electrification comes with an infrastructure investment well beyond the chargers. It adds construction complexity combined with the challenge of finding and running enough power from the grid to support charging. Several of our customers who operate CNG currently have actually found the transition to hydrogen to be much more compatible with their operation. But today at New Flyer, we proudly offer New Flyer Infrastructure Solutions as a full suite service. This team, which has grown since announcing it in early 2019, has installed and services just over 200 chargers across North America today. So talking a little bit about the transition to zero emission. During the last 3 years, we've watched the heavy duty public transit bus market grow to approximately 35% zero emission, starting with only a very few fuel cell electric vehicles. Cities who conducted pilot programs over the first 2 years are now starting regular multi-year procurements. And so the number of electric buses is growing pretty dramatically, and we anticipate that New Flyer and MCI will probably be producing roughly 27 to 30% of our production in 2022 and 2023 as zero emission vehicles. The number of fuel cell electric buses ordered also appears to be growing and keeping pace with the other types of zero emission vehicles. We've been really pleasantly surprised by the interest and engagement from our customers on the Excelsior Charge H2 fuel cell electric bus. At the current time, fuel cell electric buses are approximately 10% of the zero emission vehicles in our market and in our deliveries. So in conclusion, at New Flyer, we believe there's an appropriate solution for all 3 zero emission technologies, and that selection is really highly dependent on the infrastructure available in our cities, local energy costs, and the proposed duty cycle for the vehicles. While there's certainly a capital cost premium for both the vehicles and the infrastructure, many agencies are now obtaining enough data on both battery electric and fuel cell electric bus operation to compare the economics of the fleet at scale and enable them to evaluate total cost of ownership and determine the best mix of zero emission buses for their fleet. The new Biden-Harris administration has just announced $30.5 billion for public transit, allowing agencies to plan for resilience, remobilization, and revitalization on a long-term basis. Zero emission public transit is a priority. I'm really hopeful in the outlook for public transportation. Both the US and Canada have realized the importance of equitable, accessible, and sustainable transit, and have made milestone announcements to fund the expansion of transportation and infrastructure over the next several years in support of climate change mitigation. So I truly believe we have this wonderful opportunity in front of us to work together as enablers of a new and greener mobility area. Thank you.
Thank you, Jennifer. So at this time, I would like to get all the speakers to turn on their microphones and their video and join me on stage for our panel discussion. And just again, a reminder to the audience, please go ahead and submit the questions that you have in the Q&A button. Okay, well, thank you. Thank you very much to all the speakers, and thank you for your wonderful insights and thoughts. And let's dig into that a little bit now. I'd like to start with a question that we hear about. It's on the vehicle. So we can talk about the vehicle, then we talk about the infrastructure, and then we can talk about the fuel and other considerations. So if we start with the vehicle right now, there's a very high premium. A number of you have mentioned this for the zero emission vehicles. If we look at the light duty space, there are reports indicating that there are fewer number of parts for zero emission vehicles, and arguably the labor might be cheaper to assemble some of these going forward. So the question is, do you see the same kind of parallels, if any, between the light duty transitioning to the heavy duty? And if so, will there be a point in time where the cost of the vehicle is on parity with diesel, and if so, when? So